Good afternoon and welcome to Carlem Cymru revision sessions. This session will focus on energy transfers 1.4 and this is AS Physics. It will be presented by Mrs. Owen from Penglais Comprehensive School in Aberystwyth. The session will last about 45 minutes where the teacher will go through the relevant subject content. If you have any questions, please use the question and answer section and we will endeavour to answer your question during the session. The session will be recorded with the recording and any relevant resources uploaded to the e-sgol website in the Carlem Cymru area. Without further ado, I'll pass you over to Mrs. Owen.
Okay, hello and good afternoon, everybody. And although I will be concentrating on 1.4 energy transfer, I will take elements from 1.1, 1.2, 1.3 and 1.5 as well, as you will see, because you have to be kind of elastic with your application of your physics. Okay, so let's moving on. The qualification or the syllabus 1.4 energy concepts. This is the part that you need to know everything. We will come back to this to see if we've addressed most of the points as we go along, but this is what we are going to cover: work, energy, work energy relationship, power, and dissipative forces and efficiency. So without further ado, let's have a look at a few energy types that we already know about and that we have equations for. So, I mean, these are taken from GCSE and you are expected to be able to know and identify them and apply these equations at A level. So we've got kinetic energy, half mv squared, half the mass times by the velocity squared, or you can work out mass times velocity squared and half the whole lot. Gravitational potential energy, we often show it as change in gravitational potential energy, so that's why that triangle is there, equals mass times gravitational field strength times the change in the height. Elastic potential energy, there's two equations there that you might know and might recognize: half Fx, half force times distance, like stretched or compressed, or it can be equal to half kx squared, where k is the spring constant and x is either the extension or the compression. And let's not forget that we remember work is force times distance, but actually more accurately we should remember force times distance times cos theta, where if we have got us doing moving an object force in a direction x, it's straightforward, but if for some reason we apply it at an angle, we've got to work out what the component is in the direction that we want to know about. So we're applying a force, but it's at an angle to the direction in which it's moving in. So we say F cos x to give us that component in the direction, and then times that by the distance to give us the work done if we are moving in this direction. Okay, so that's why the cos x comes in. So looking at this, candidates really are encouraged to apply the types of energy to different situations. So it's a very fluid thing. You're expected to apply the conservation of energy law, so being able to change one energy into another. And if it's not exactly what you expect it to be, then maybe it's turned into other forms because it's had to do work against, say, resistive forces. So you need to kind of like identify from the energies that you've been given, you know, what is the useful energy, what's the wasted energy, what's the input energy, and then able then to work out the efficiency of the system. So it's very fluid. It's not kind of like, for one given example, it's not set in concrete. You have to be able to change from one thing to another. All right, and let's have a look. So I'm going to apply this to a certain situation. Now, here we are. We have got a ball, Y, and what we're going to do is we're going to pull it away at an angle, theta, to the vertical, and we're going to release it in order to hit a ball X on the top of a paper cup, and it's going to fly hopefully into another paper cup set on the floor. So this is really quite an involved and detailed set of equations that you have to kind of like be able to apply, and they're not just energy equations. So I'm going to break it down, okay, and consider, first of all, I got my ball Y and it's got gravitational potential energy, and that gravitational potential is given by the mass times by the g times by the change in the height. And that gravitational potential energy, once we release ball Y and it knocks into X, so at this point we'll have no more gravitational potential energy. So the gravitational potential energy that it has here will be lost, and that will kind of like get converted into kinetic energy. So all of that gravitational potential energy will convert into kinetic energy. So whatever the gravitational potential energy loss is, gets converted into a kinetic energy gain. So you always have to ask yourself, is it a gain or is it a loss that we're having? And sometimes it's easy to look at it as the change in gravitational potential energy so that we can get this idea, is it a gain or is it a loss? Okay, so in order to do that, now we know kinetic energy is equal to half mv squared. So we can relate these two together to kind of like get an idea of what the velocity is going to be. Because the whole aim of this experiment is to try and find this distance here where I'm going to put the cup. And the measurements that you've been given are the length here and the angle here. Those are the only two measurements so far that you're being given. So let's move on a little bit more. We've had a look at the energy changes, and there is an assumption here, a big assumption, is that all of the gravitational potential energy is going to be converted into a kinetic energy gain. And that is not necessarily true, and I will address that in another smaller problem for you to see. Okay, so let's start with then, you have got length and you've got the angle, and we've got to work out what this change in height is to work out this gravitational potential energy. So we can simplify that diagram by just kind of like putting a dotted line all the way across and making a right angle triangle. So what we have now is a triangle, and this distance here is the change in height, and we've got length L here and we've got theta here. Remember that B is where the ball is, A is where the ball ends up. So this whole length here is also equal to L. But we can use trigonometry to work out what this distance OC is. So OC is given by the adjacent to the angle. So we can use, if we've got the adjacent and we've got the hypotenuse, we can use cos theta equals the adjacent OC divided by the length, the hypotenuse. Okay, I'll put that like that. Remember car, soa, saw, toa. All right. So cos adjacent over hypotenuse, OC over length. So L cos theta equals OC. So this part here is L cos theta. So all I have to do now is take L cos theta away from L to find my change in height. So I get that L minus L cos theta. Now, you might think, well, I could have measured that change in height, with a ruler, but it's actually probably more accurate to measure the length of the string that you've got and measure the angle with the protractor. The length of the string here would be probably plus or minus, and I'm looking at uncertainties now, plus or minus 0.2 of a centimetre. Why do I say that? Because it's difficult to locate the centre of the ball. So I'm not going to go to the smallest resolution of my ruler. All right, so the length can be written, say, plus or minus 0.2. And if I want to find out the percentage uncertainty, then I would have to do the 0.2 divided by whatever your length is and times by 100%. Okay, now with the angle, the uncertainty in the angle could be plus or minus. Now I would here go with the smallest division, because you haven't got, even though you can't get the center, there very easily, you can line up the protractor to get a good reading, even if you have to move the protractor around. So that's measured in degrees. So that would be plus or minus 1 degree. So again, if you wanted the percentage uncertainty in theta, we take the smallest division, the resolution, all right, and we go divided by your angle for your theta here, and then just times it by 100%. Okay, I just want you to have awareness of your uncertainties as we go through this, all right, as well as doing the mathematics. And we could do that at the end, or we could do it as you're going along. Right, so now what we've got is, we have got, if we go back up, we have got the change in height. What have I done? Not that one. I want to go up. The change in height is given by L minus L cos theta. All right, so now what I'm going to do is I'm going to get my equations for gravitational potential energy and kinetic energy and relate the two together. So mg delta h equals half mv squared. And you notice here that it doesn't matter what the mass is of the ball that's falling, so that cancels out. And I can rearrange this g delta h times by 2 equals v squared, because I'm dividing 2 on this side, so I take it over to the other side, times by 2. And then because I've got a square here, I'm going to have to square root on the other side. So square root 2g delta h equals v. Now I've got a value for delta h here from knowing the length and the angle, so I can put in square root 2g brackets L minus L cos theta. Yes, you can take L out, so you could have L brackets 1 minus cos theta equals V. Now, nobody's expecting you to remember these equations, but you are expected to identify the energy types and to be able to relate one energy type to another, because the conservation of energy law is a very fluid thing. Energy cannot be created nor destroyed, only turned from one form into another. So you have to be able to kind of manipulate these equations and be able to change from one side to another to get something else. So out of this, we want this velocity, because it's this velocity here which gives us a horizontal velocity in this direction. Now, there is another assumption to be made. The assumption is that the collision between y and this ball x, which is going to go flying off into a cup, hopefully, is that it's an elastic collision. Now, by that, what we mean is that all of the energy that the y had as the kinetic energy is equal to the kinetic energy of x, i.e. no energy is lost to other forms. You'll always have conservation of energy. It's just in this particular case, you'll have conservation of kinetic energy. All right, perhaps I ought to put that there for you. Conservation of kinetic energy. You'll always have kinetic conservation of momentum in a collision. That happens in every collision, but just in very special elastic collisions, the kinetic energy will be conserved. Okay, so it means that whatever the horizontal velocity of y means that means if it's the same mass for both ball x and y, then we can say that the horizontal velocity of x is the same as the horizontal velocity of y. So now what we've got is a situation, try and remember that equation. I'll try and pull it up. Now we've got the bottom half. So what we've got is a horizontal velocity going this direction. And we've established that that is square root 2g L minus L cos theta. Remember, the only two measurements that you were given is the angle and the length. Now, what we need to also measure is the height. So that is our third measurement, all right? And that height there can be quoted to plus or minus. Now, again, it will be difficult to take it to the center of the ball at the top. So I would probably go on this one. And also you might have parallax error in getting the ruler quite close. So you can go plus or minus 2 millimeters, and there could be a range here of 2 to say 5 millimeters. And if you wanted then to find the percentage uncertainty in the height, because we're going to need this a little bit later to find out the percentage uncertainty in that final value of d that we're going to calculate. So the percentage uncertainty in the height is given by 2 over whatever the height is, the mean height, not the smallest, not the biggest, but if you had to repeat it several times, you'd take the mean height and then times it by 100%. Okay, all right, so now we've got to look at it in terms of those equations of motion. Now let's have a look at the vertical motion only. So with the vertical motion, we have initially uv here is 0. Yes, it's going horizontally. Yes, it's got a horizontal velocity, but because it's at rest and it's being being hit so that it'll fly off kind of horizontally, it hasn't initially got any vertical velocity. We don't know what the final vertical velocity is, but we know also that the acceleration is the acceleration of free fall, which is g, which is 9.81 meters per second squared. We know that. And we want to find and we also know h, that's the distance dropped through to get to the floor. So we'll call that h here. Okay, so we don't know the final velocity, and actually what we want to find here is the time, because the time it takes to go vertically will be the same time as it takes to go horizontally. So, and that's the only link between horizontal and vertical motions, because if we drop anything either straight down or at a, if we fire it horizontally, then one will go horizontally and take this projectile path, the other one will go straight down and it will land in the same time. So if you've got two balls doing that, it will go click, 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 and they will go in tune with one another so that you can tell that they're taking the same time to go horizontally as it is taking to go vertically. Okay, we say that there is no forces acting horizontally. but the force acting vertically is the acceleration of free fall due to the Earth's gravitational field, so that we have to use the 4 equations of motion to solve any problems vertically. So we have to split it up in projectiles. Okay, moving on. So the equation I'm going to choose is S equals ut plus half a t squared. This applies to the vertical motion only. U is equal to 0. And if ever you have to do this in an exam question, just do make sure you put u equals 0 somewhere before you start crossing out. Okay, and a equals g before you substitute. So the height here is given by half a g t squared. I can use s, I can use h, it doesn't matter. And let's rearrange it. So half, so divide by 2, bring it over to the other side, becomes 2h equals gt squared. And then bring the g as times, so take it to the other side, becomes divide, so 2h over g equals t squared. And then square root 2h over g equals t. Okay, now, once you've got the time now, the horizontal velocity and the horizontal motion is actually a lot more straightforward, because with the horizontal motion, because there are no forces acting, we don't have to use the 4 equations of motion. So we can use the horizontal velocity equals the horizontal displacement divided by the time taken. Now we've got the horizontal velocity, we've got the time taken, so we can work out that horizontal displacement, which is equal to d. Okay, so let's rearrange this. The horizontal velocity times by the time is equal to the d, the distance where we would have to put the paper cup directly below x. And we have got a few equations that we can put in place of that. So the time equation, we have got square root 2h over g times by, we've got the equation for the horizontal velocity, which was 2g L minus L cos theta, all right, equals d. Now, if you were in my class, you'd actually try and work out all of those calculations. You wouldn't look at uncertainties just at this point, and you would then, present me with a number. And if you present me with a number of, say, 63 meters, I'll be saying, perhaps you need to look at your powers of 10 that you've used and go back and give me a sensible answer. So do have a look at your answer to see if it's sensible. And the way to get around this is just make sure, for example, the height here is in meters, can't be in centimeters, because if it's in centimeters, then the time won't be in seconds, because g is given to you in meters per second squared, all right? And we work in SI units. Have a look at this is a common mistake, that the length here won't be quoted to meters, it will be quoted to centimeters. Okay, so if it's not in meters, then you're not going to get a final distance here, which is in meters. All right, so you'll be expecting somewhere between, say, 0.5 and 1 meter. And if it isn't, there's probably something to do with your power of 10 errors. Okay, so now let's have a look at the uncertainties in that value of d before we move on to another problem. And just have a look at this, because I'm just going to rewrite this a little bit. And I'm just going to put 1 square root out. So 2, I think, I just want to check that I've got my, yeah, I've got it right. I'm just checking. So 2g, now I'm going to take the L out of that because it's the L's twice, all right? So L, 1 minus cos theta, all right, times by 2h over g. Oh, well, the g's cancel. Okay, the 2's can be combined together, so that's 4. So square root 4 is 2, so that comes out of the brackets. And I'm left with L, 1 minus cos theta, times by h equals d. Okay, right, now we've got a percentage uncertainty in L. we've got a percentage uncertainty in theta. We've got a percentage uncertainty in h. Now, you might think to get the percentage uncertainty in d, it's a simple case of adding them up. Well, here it's slightly different because that square root, when you write it in an exponential, so for example, it'll be L to the half, all right? Because square root is basically, if I square root x, then that is x to the half. All right, so 1 minus cos theta to the half and h to the half. That means the percentage uncertainty, we have to times it by half. And then we can add the percentage uncertainty in theta as long as we times it by a half. I've got 2 in my head because very often when you do things like, for example, pi r squared, if you had the percentage uncertainty in r, then you would times it by 2 because you're using it twice. But it is what we've got to do here with the square root is it's to the power of a half. So we have to times it by a half. All right, and then again times the percentage uncertainty in the h by a half because they're all in the square root, and that will give you your percentage uncertainty in d. You cannot add uncertainties, you know, the raw uncertainties. You have to work out the percentage uncertainty and then you can add the percentage uncertainties up, as long as you've multiplied it by the exponential that they are in the equation to work out the final value. And once you've worked out the percentage uncertainty in D, you'd have to divide that by 100, all right, to get the uncertainty, percentage uncertainty D, divided by 100, and then times that by whatever the D value is, okay, in order to get the uncertainty in D. Okay, right. I think you'll agree that that's quite a lengthy kind of synopsis of kind of, you know, kinematics has come into it, momentum and elastic collisions has come into it, uncertainties, energy transfers and energy changes, and even vectors in terms of, you know, components or and working out using trigonometry. Okay, so let's go on to a smaller problem. Right, now I'm thinking this one, I've seen very often this question of, you've got a parachutist, all right, I know, not a very good parachutist, but there he is, and he's at a certain height. So as he moves down, he's going to be losing gravitational potential energy. And as he loses this energy, he's going to gain kinetic energy. Now, let's say that you have been given 2 values. You haven't asked to work them out at all, and you've been given a height change of, say, 2,000 meters, 2 kilometers, where he's falling from. Now, if you've been given a value for both of these and they are not the same, then that means that energy cannot be created nor destroyed, only change from one form into another, but it could be more than one type that it could be converted into. So, for example, that gravitational potential energy loss, take away the kinetic energy gain, would be some sort of energy that has been converted into, because most probably it has the person falling has had to do work against air resistance. So we'll say work done against air resistance. Now be careful here, because you cannot say that the loss of gravitational potential energy loss, take away the kinetic energy gain, is, for example, air resistance. because energy is not equal to a force. But if you times that force by a distance, you get work done. And then you can look at, okay, it's work done. And what are you doing work done against? You could be doing work done against gravity if you were lifting it against gravity. You could be doing work done against air resistance, like in the case of this example that he's passing through the air. So be careful. Now, if they are wanting an energy, then you can say, you know that work done is the same thing as energy transferred. So you can, if you really want to give it an energy or an energy name, you can say that it's work done against energy to give you, say, heat energy. Usually the wasted energy is heat or sound. So you could say heat energy and sound energy, all right? Or you could just leave it as heat energy, but just don't fall into the trap of saying it's air resistance when it's the work done against air resistance. Right, okay, yes. Oh, I'll do that if I've got enough time. I want to give you another example. Another example of a stretch spring. So can I, yeah, okay, right. Can I, okay, I've got a little problem, and it's a lovely little problem. I've got my ruler stuck to the floor. I've given this to my lower six, and I'm sure you've seen this before. And I want to measure the height of the room. Unfortunately, though, my ruler is stuck to the floor. I can't move it. But I have got a spring. Now, we usually use an elastic band, but let's use a spring here. And the only reason why I'm going to switch to a spring is because the spring constant for a spring is constant, but for an elastic band, it does change because it's non-linear. It's got different. It's not constant, put it that way. It's not constant. So let's go with a constant one just to make life a little easier. So you've got a spring and you've got a ruler that's fixed to the ground, which is 1 meter tall. And how are you going to measure the height of that ceiling? Well, you can look at it in terms of energy transfers. If I pull this spring hard enough from the top of the ruler, or a rubber band from the top of the ruler, then you're going to give it elastic potential energy. And all of that, let's assume, okay, big assumption here, that all of that elastic potential energy, when it has, yes, it will convert into kinetic energy initially, but then it will go flying up to the roof, and you want to give it enough pull, enough stretch just to hit the ceiling, not so that it lies flat and not so that it falls short. So you want to give it enough so that it just hits the ceiling, so that the elastic energy is all converted into gravitational potential energy. Now, this time, when we stretch it and release it, it's the elastic potential energy that's going to be lost. And it's the gravitational potential energy that's going to be gained. So you can see that in different situations, you're going to have different scenarios, and it's for you to identify the types of the energy and the energy transfer involved. So in this particular case, we're going to assume that all of the elastic potential energy is the gain in the gravitational potential energy. Now, notice I'm not worrying about kinetic energy, because although the elastic potential energy is converted into kinetic energy, then it gets converted into gravitational potential energy. And all I'm doing is I'm looking at the first and I'm looking at the last. I'm not looking so much at what's happening in between. So we can say that using the equations, half kx squared is equal to mg delta h. We can rearrange that. Now we will have to have the mass of the spring or the rubber band that you're going to use. So in order to do that, it's wise to use just not one spring, but kind of like several springs, because they are quite light. All right, say 10 springs, and then divide it by 10 to get the value of 1, and you will have a more accurate value for 1, unless that's if the mass is very, very small. It could arguably be that all of the springs are different masses. I'm assuming that they are all the same. Right, so we can now, to get the height, we want this change in height here. We've got G is 9.81. Now we've got X, because that's the extension that we pull it to. Okay, because we can use this ruler here, we can measure the original length here, and then we can measure the extension that we're going to pull it at, just so that it hits it. So you want to kind of like be doing a trial and error method, so that you're going to just touch that ceiling. And then K, now you're going to have to work out K by using force against extension for a set lot of weights, so 1 Newton all the way through to 6 Newtons, to plot a graph to find the gradient. So F, the change in F over the change in X, will give you the spring constant K. And once you've got that, you can put it into the equation, and we can rearrange it to find the change in height. So the change in height, I always like to, if I want to find the change in height, I always leave it on that side, and I move everything else relative to it. So mg is times it by change in height, so I divide it on the other side. So I have half kx squared over mg, and then let's just tidy that up. Kx squared over mg equals the change in height. Okay, right, so, but don't forget, change in height is from here. So this will be the change in height from here up to here. So we will have to add the change in height plus 1 meter to get to the height of the ruler. And the same occurs here as with all of your physics problems. Make sure X here is the extension in meters. And if you don't convert it, it's okay. You can just put a slash and then times 10 to the minus 2 meters, say, if you've been working in centimeters. It's just that the K needs to be in newtons per meter, say, so that when you actually calculate and use those standard SI units of meters, then you will get the meters coming out of it. Okay, now I have got a few more minutes, and there are a couple of things that I'd like to go over. I'd like to look at uncertainties in this particular experiment, and then I might extend the other experiment that we've done. Now, but first of all, can I go back to Mr. Rith? Can you tell me, is there any questions from the floor?
No questions at this stage, Mrs. Owen, thank you.
Okay, so I can carry on, can I?
Yes, you may. Yes, please.
All right, okay. Right, now I'm going to look at uncertainties, all right, in this particular experiment. So let's have a look at it. X. Now, X is the extension, and the extension you can get to the nearest division, and the nearest division will be the smallest, the resolution of the ruler. So let's go with 1 millimeter. Now you can write it like that, or you can say 0.1 centimeter, or you can say 0.001 meter. Okay, and then to work out the percentage uncertainty in X, you can get, it depends how you've written your X, whether it's in millimeters or meters, but just be consistent with what you use. So let's just say for X is here is say 15 centimeters. So I'd write it like this as 15 centimeters. My percentage uncertainty in X therefore will be 1 millimeter. Now this is in millimeters, this is in centimeters, so make sure sure that you put them in the same. So for example, 0.1 centimetre divided by, say, 15.0 centimetres, so that ties in with that, and then times by 100% to get the percentage uncertainty in your X. Okay, so that's X. My percentage uncertainty in G won't have anything because it's a constant, so no uncertainty in G. We don't have to worry about that. Let's have a look at my mass from my mass balance. Well, my mass balance could read to the nearest 0.01 of a gram. So let's say that the mass, I'll just do the mass of 1. So let's say the mass of percentage uncertainty in my mass would be, for example, 0.01. Let's say it was 3.2 grams or 3.21 grams. Why? Because the 3.21, so that ties in with that. So I've quoted my measurement to the near with the same resolution of the uncertainty times by 100%. That will give me my percentage uncertainty of mass. Now, we need to look at this K value. Now, K value we've got from my F and these X extension values. So for sake of argument, what you have to do here is, because you're using, when you go on to year 13, we do error bars and we do lines of worst fit, and then we develop that into getting an uncertainty in the gradient. But just for here for now, because I've worked out K using the force divided by X, let's say that the percentage uncertainty in the K value is equal to the percentage uncertainty in the F value plus the percentage uncertainty in the X value. So once I've got this percentage uncertainty in the K value, to get the percentage uncertainty in delta H, because delta H is given by kx squared over mg, then if we want the percentage uncertainty in H, we will have to do this percentage uncertainty in K, because we're using it just once in the equation. Add percentage uncertainty in X, but we're using it twice because we're doing X times X. So we times that by 2. And then to that, we add the percentage uncertainty in the mass. Okay, and that will give you the total percentage uncertainty in the height. Okay, so we kind of like looked at errors. We've looked at uncertainties, which is the smallest division in some cases, and in other cases where the reading is moving, or it's difficult to ascertain the full reading because of parallax error or finding the center of something. Then we've worked out uncertainties, and then we worked out kind of percentage uncertainties, and then you add those percentage uncertainties in order to work out percentage uncertainty in a calculated quantity. Now, I don't know if I've got time, but I would like to go back. Actually, no, I think it's time really to recap. All right, and let's see if we've addressed and how much we've addressed. Okay, so work is a product of force times distance moved in direction of the force. You can give this equation Fx cos theta if it's at an angle to this direction. We have looked at potential energy, elastic potential energy, and kinetic energy, and we've looked at the conservation of energy and making sure that we're fluid and we can apply the energy changes. We have addressed this work-energy relationship. I didn't do it exactly like this. They've done it here of different kinetic energies. So kinetic energy before and after, and then doing work against a resistive force. And then that leads on to power is the rate of energy transfer, so the energy divided by the time. We've looked at dissipative forces as in air resistance and doing work against air resistance, and that reduces the overall efficiency of a system. And the last thing would be the efficiency of a system, identifying the useful, identifying the total, and working out the efficiency out of that system. And I think actually you can sort of get that from the equation that we've done here, because sometimes people do this for real, like in class, and they realize they have to put their cup here. So actually the efficiency of the system is such that perhaps the ball has had to do some work against something else, maybe deforming the other ball, or sound energy, or doing work against resistance or something, so that clearly that there is efficiency to be worked out there. I think on that note, and using those equations there as the final bit, I think we have come now to a close. Thank you very much for listening, and I'll catch up with you again next week.